Jai Hind everyone, I am from Indian Space Team Rocket Science Division. Ever wondered how hybrid rocket engines work and why they're so fascinating? Well, you're in for a treat. These marvels of engineering are a blend of solid and liquid rocket engines, representing the best of both worlds. They play a crucial role in space exploration, and their unique combustion process is a testament to human ingenuity. So buckle up as we delve into the intricate and mesmerizing world of hybrid rocket engines. Prepare to dive into the world of hybrid rocket engines, where chemistry meets physics in a spectacular dance. Hybrid rocket engines are a marvel of engineering, combining the best of solid and liquid rocket engines. These engines are not just a hybrid by name, but also by nature. They elegantly merge the characteristics of both solid and liquid rocket engines, using a solid fuel and a liquid or gaseous oxidizer. Now imagine the power generated when these two components combine. The result is a force that can propel spacecraft into orbit or even beyond. But what makes these engines stand out? Well, they offer a unique blend of advantages that make them a compelling choice for rocket scientists. For starters, they significantly improve safety. The separate storage of fuel and oxidizer reduces the risk of accidental ignition, a concern often associated with solid rockets. In addition, hybrid rocket engines present fewer handling and storage issues. The ingredients in solid rockets can react chemically or thermally, leading to potential complications. However, in hybrid rockets, the solid fuel remains inert until the oxidizer is introduced, mitigating these risks. Perhaps the most attractive feature of hybrid rocket engines is their controllability. They can be easily stopped or restarted, and their thrust can be adjusted mid-flight. This level of control is a rarity in solid rockets, which once ignited, burn until their fuel is exhausted. So we know what hybrid rocket engines are, but how exactly do they work? The magic of hybrid rocket engines lies in the combustion process. It's a fascinating dance of science and engineering that propels these engines to reach the stars. To simplify, we can think of combustion as a lively party where fuel and oxidizer are the main guests. The more oxidizer we invite to the party, the faster the fuel burns. This relationship is governed by a special equation that indicates the fuel's regression rate, essentially its burning speed, is proportional to the oxidizer's mass flux rate, the rate at which oxidizer is flowing. This differs from a solid rocket motor, where the fuel's regression rate is proportional to the chamber pressure. In a hybrid rocket engine, it's all about the oxidizer's flow. The fuel's burning speed is not dictated by pressure, but by the oxidizer's presence. As the motor burns, it's like the party's getting bigger. The fuel port's diameter increases, and so does the fuel mass flow rate. Imagine more fuel is joining the party, but to keep things balanced, we need to invite more oxidizers too. This dynamic interplay is what we call the oxidizer to fuel ratio, or OF for short. Now, the OF ratio doesn't remain constant. It changes over time and also varies based on the position down the fuel grain. The closer to the top, the higher the OF ratio, and somewhere along the grain, there may exist a point called the stoichiometric point, where the fuel and oxidizer are in perfect harmony for combustion. This simplified explanation of the combustion process, with its ever-changing dynamics and balances, is the heart of a hybrid rocket engine. It's a complex dance, a party of elements, all working together to produce the powerful thrust that propels the rocket upwards. Controlled yet powerful, this combustion process is what powers our journeys to the stars. Now that we understand the combustion process, let's delve into the properties of hybrid rocket engines. One of the defining characteristics of hybrid rocket engines is how the oxidizer to fuel ratio, or OF, varies. This ratio is not static, but changes based on two factors: time and position down the fuel grain. As the rocket motor burns, the diameter of the fuel port increases. This results in an increased fuel mass flow rate, which in turn alters the OF ratio. This shift during the burn is a unique trait of hybrid rocket engines. However, the increased fuel mass flow rate can be balanced out by also increasing the oxidizer mass flow rate, keeping things in check. The OF ratio also varies depending on the position down the fuel grain. The closer the position is to the top of the fuel grain, the higher the OF ratio. This means that as the fuel grain burns and the position moves down, the OF ratio changes. Now, this might sound complicated, but it's all part of the hybrid rocket engine's design. This variation in OF ratio can actually be beneficial. It allows for a stoichiometric point to exist at some point down the grain. This point is where the OF ratio is ideal for combustion, maximizing the efficiency of the burn. But what does all this mean in practical terms? Well, these properties make hybrid rocket engines incredibly versatile. They can be designed to burn at different rates and for different durations, depending on the specific needs of the mission. This versatility makes them a valuable tool in our quest to explore space. And it's not just about versatility. The shifting OF ratio also contributes to the safety of hybrid rockets. Because the burn rate is dependent on the oxidizer flow, it can be controlled much more precisely than in a solid rocket motor. This makes hybrid rockets safer to handle and operate, further enhancing their appeal. These properties make hybrid rocket engines a versatile tool in space exploration. Like all technologies, hybrid rocket engines come with their own set of advantages and disadvantages. Let's delve into these to get a clearer understanding of the full picture. Hybrid rocket engines are often hailed for their improved safety features. They have fewer handling and storage issues compared to their solid rocket counterparts. The ingredients in solid rockets are often chemically and thermally incompatible. Fluctuating temperatures can distort the grain of the fuel, leading to potential hazards. This is where hybrid rockets shine. They handle temperature changes better, reducing the risk of fuel breakdown or decomposition. Moreover, hybrid rockets are more controllable. They can be stopped, restarted, and their thrust can be throttled. This is a stark contrast to solid rockets, which rarely have these capabilities. This level of control makes hybrid rockets a desirable choice for many applications. However, no technology is without its hitches. Hybrid rockets also come with their share of challenges. One such challenge is the oxidizer-to-fuel ratio shift, also known as the OF shift. With a constant oxidizer flow rate, the ratio of fuel production rate to oxidizer flow rate changes as the fuel grain regresses. This can lead to off-peak operation from a chemical performance viewpoint. Another disadvantage lies in the regression characteristics of hybrid rocket engines. These often drive the need for multi-port fuel grains, which can have poor volumetric efficiency and structural deficiencies. Refueling a partially or totally depleted hybrid rocket can also pose significant challenges, as the solid propellant cannot simply be pumped into a fuel tank. This can be a crucial factor depending on how the rocket is planned to be used. Moreover, the development of hybrid rockets is not as advanced as that of liquid or solid rockets. However, it is believed that further investment in research and development could rectify some of these challenges. Despite these challenges, hybrid rocket engines continue to be a promising field in rocket science. We've journeyed through the intricate world of hybrid rocket engines, but what's the takeaway? Well, first and foremost, it's clear that the combustion process in a hybrid rocket engine is a complex dance of variables. The governing equation for hybrid rocket combustion shows that the regression rate is dependent on the oxidizer mass flux rate. This means the rate at which the fuel burns is directly proportional to the amount of oxidizer flowing through the port. Quite different from a solid rocket motor, where the regression rate ties to the chamber pressure. As the motor burns, the diameter of the fuel port increases, resulting in an increased fuel mass flow rate. This shift in the oxidizer-to-fuel ratio during the burn can be compensated for by increasing the oxidizer mass flow rate. This point alone indicates the complexity and precision involved in the operation of hybrid rocket engines. We also explored the properties of hybrid rocket engines, which bring with them both advantages and disadvantages. For instance, they have fewer handling and storage issues compared to solid rockets. They are also more controllable, with stop, restart, and throttling features easily incorporated into most designs. However, they also come with their share of challenges. The oxidizer-to-fuel ratio shift, or OF shift, can lead to off-peak operation from a chemical performance perspective. Poor regression characteristics often drive the need for multi-port fuel grains, which can lead to structural deficiencies and poor volumetric efficiency. Despite these challenges, it's important to remember that hybrid rocket engines are still a relatively new technology. Much less development work has been completed with hybrids than with liquids or solids. So, it's likely that some of these disadvantages could be rectified with further investment in research and development. So, there you have it. A brief yet detailed tour of the world of hybrid rocket engines. The next time you marvel at a rocket launch, remember the intricate dance of chemistry and physics happening within the hybrid rocket engine.